Hi students, this is your introduction to solid mechanics class. The subject code is CEES 402. Now we are going to learn about torsion. What is torsion? You know that the torsion is basically a twisting moment. Okay, to transmit energy by rotation, it is necessary to apply a turning force. Suppose this is a shaft. This is the turning force or twisting moment. And in case of shaft, if the force is applied tangentially in the plane of transverse cross section, the torque or twisting moment may be calculated by the applying of force with the radius of the shaft. Suppose this is a cross section of the shaft and this is the tangential force F and the radius is R. So twisting moment, that is T, is becomes F into this radius R. Okay, if the shaft is subjected to two opposite turning moments, then it said to be pure torsion. Okay, and it will uh, have the tendency of shearing off and every cross section which is perpendicular to the longitudinal axis. Now we are going to prove the equation of torsion. We have already learned this equation, that is m by I equals to sigma by y equals to E by R in case of bending. In case of bending stress chapter, in bending stress chapter we have already proved this equation. So similar to this equation, there is another equation which is related to torsion. Now we are going to prove that equation. The name of the equation is, one second, is torsion equation. Now in this torsion equation is based on some assumptions. Okay, so now the assumptions of torsion equation, that is the material of the shaft is uniform throughout. That means throughout the shaft there is no change in density. The shaft circular in section, that means cross section, remains circular after loading, that is after applying the twisting moment. A plane section of shaft normal to its axis before loading remains plane after the torques have been applied. The fourth one is the twist along the length of the shaft is uniform throughout. Number 5. The distance between any two normal cross section remains the same after the application of torque. Okay. And last one is the maximum shear stress induced in the shaft due to the application of torque does not exceed its limit value. So let's start. Let sorry capital T is the maximum twisting torque. D is the diameter of the shaft. J is the polar moment of inertia. Okay, and tau is obviously the shear stress. G is the modulus of rigidity. Theta is the angle of twist, and finally the length. L is the length of the shaft. So now suppose this is the shaft. This is a circular cross section. Okay. Yeah. There is a center line. Diameter is capital T. Okay, so this end of the shaft of this shaft is fixed. This end is fixed. This is the length of the shaft, that is L. Now we are taking an imaginary line. Suppose this, that is, suppose capital L. This is capital M. LM. We are taking a imaginary line on the shaft, that is LM. Now we are going to apply a twisting moment, a torque or twisting moment, that is T, in a clockwise direction. So by applying this torque T, this point M will shift. Suppose the M will shift into this point, and we are taking this point as M dash. Now joining the line, that is L to M dash. Okay, this is a cross section of the free end. This is the center of the shaft. We are taking the point as O, joining this center also. This angle of twist is the angle is theta, but here this angle is, we are taking this angular value is, we are assuming phi. Okay, this one is theta and this one is phi. So here the shear strength, that means the phi is the shear strength. So phi becomes equals to m dash by the length. This m dash is the length of the arc into the length of the shaft. This is the arc length and this is the length of the shaft, L. Also we can write, that is phi equals to tau by G. Tau is the shear stress by the rigidity modulus. So now we can equating these two equations, that is m dash by L equals to tau by G, and this we can write the m dash as r theta. From this cross section we can write m dash equals to r into theta. R is the radius of the shaft, that is half of d. This is r. Okay, so r theta by L equals to tau by g. So we can write tau by r equals to g theta by L. This is equation 1. Now here we can see this is the cross section of the shaft, and we are taking a elementary thickness or elementary ring on the cross section at a distance x from the center point O, and the thickness of the cross section elementary strip or elementary cross the strip is dx. Okay, so now the turning force on this elementary ring, the turning force on the elementary ring, that is tau x. Tau x is the shear stress along the distance x. Tau x is the shear stress along the distance x into area 2 pi r into dx. Why 2 pi x into dx? This is the value of the area. This 2 pi x into dx is the value of the area of the elementary ring, because this elementary ring is a circular section. Now if we attach if we 2 pi x, this is the length, this one is the thickness. If we bend this rectangular strip of length 2 pi x and thickness dx, it will form this kind of elementary circular ring. So that's why we are taking this as a area. Now the turning moment on this elementary ring, suppose that is TD is equals to, suppose this is the turning moment on the elementary ring, that is equals to the force 2 pi x dx into the distance, that means from center to the elementary ring, that is x. This is the turning moment on the elementary ring, that becomes 2 pi x square dx, that is TD. Now comparing the shear stress at a distance r is tau and the shear stress at a distance x is tau x. So by comparing the stress and the radius with this relation, we can write tau x as tau into x by capital R. So now we are going to substitute this value tau into x by R into this equation. Okay, so that becomes tau into x by R into 2 pi x square dx. So now we are going to integrate both this left hand side and right hand side. that is integration 0 to t td is equals to tau by r into 2 pi integration 0 to capital R x cube dx. Okay, so that becomes, here it is t, and from this integration we get 2 pi tau by r into r to the power 4 by 4. Okay, we know that the moment of inertia, that means the polar moment of inertia for a circular shaft, that is J equals to pi by 32 d to the power 4 or pi by 2 r to the power 4. Okay, this thing we already know, the relation we already know. So we can rearranging this equation and then write, that is, one second. Okay, that is t. Now we can write t equals to tau by r into pi r to the power 4 by 2. So this becomes the J, the polar moment of inertia. So that becomes tau by r into J. Okay, so we can write T by J equals to tau by r. This is the equation 2, and from equation 1 we can write, from 1 and 2 we can write T by J equals to tau by r is equals to g theta by L. This is the torsion equation. Thank you. So our torsion equation is T by J tau by R equals to g theta by L. Torsion equation. Okay, so one thing that I have left, that is polar modulus. So the relation T by J is equals to tau by R. We can write T equals to tau into J by R. T equals to tau into J by R. This J by R is known as the polar modulus, and this polar modulus is represented as Z suffix P. Z suffix P equals to J by R is the polar modulus.